Okay, so these are the solutions for coursework exam number 1 for Math 1141. So it's a pretty short exam. The first question here asks us to determine whether the lines L1 and L2 are parallel, intersecting, or skew. Okay, so we have here two lines. I'm just going to write back these two lines here. So line 1 is given as 2, -1, 3, plus 1, 2, -1, s, and L2 is given as 0, 4, -2, plus 2, -1, 1, t. So they ask us if it's parallel, intersecting, or skew. So first thing I noticed that is the two direction vectors are not scalar multiples of each other, so the lines are not parallel. But they specifically ask us firstly if it's parallel. So we must at least write a little bit of a line here that says it's not parallel. So we can call the vectors something. So I'm going to call it, so I'm going to say since vector 2 v2, which is 2, -1, 1, is not a scalar, multiple of v1, which is 1, 2, -1, then the lines are not parallel. Okay, so that part is taken care of. Now we have to determine if the lines are intersecting or it is skew. Okay, so we need to take these two lines here that I have, and I need to form some simultaneous equations and then solve them for s and for t. Okay, depending on the values that we get for s and t will let us know whether the lines are intersecting or skew. All right, so let's set these equations up firstly. So from the first line L1, I'm going to multiply throughout like this. So I'm going to say S. So I'm going to start from L1. Okay, I'm going to say 2, which is here, plus 1 by S is equal to 0 plus 2 by t. And I'm going to do that for all the elements of L1 and L2. So we have 3 simultaneous equations. So the first one is 2 plus s is equal to 2t. The second one is -1 plus 2s is equal to 4 minus t. And the third one is 3 minus s is equal to -2 plus t. So let's label these equations so we can keep track of them. Okay, now at this point, the choice is yours, how you decide to go ahead and solve these equations. I'm going to take equation 1. So I'm going to say from 1, I'm going to have 2 plus s is equal to 2t. Which means that I'm going to divide both sides by the number 2. So I'm going to get 2 plus s all over 2 is equal to t. I'm going to simplify. I'm going to get 1 plus s all over 2 is equal to t. So now I have what t is. It's in terms of s. I'm going to call this another equation, maybe 4. And now I have to take another equation. So I'm going to take 4 and I'm going to put it into, you could put it into any equation that you want. I'm going to choose equation 2, right? Since I choose 1, I'll just go down. So I'm going to say take 4 and sub it into equation number 2. So I'm going to get negative 1 plus 2s is equal to 4 minus t. And my t here is 1 plus 2s. So I'll have 1 plus, sorry, not 2s, s all over 2. Then I'll simplify. So I have negative 1 plus 2s is equal to 4. So we could actually subtract this immediately. So 4 minus 1 is 3. And the negative sign will come on the inside here. Then I'm going to transpose this 3. And actually, let's bring this negative 1 right here on this side. So you'll have 3 plus 1 is 4. And then 2s plus s all over 2. Equal sign. And 2s plus s upon 2 is 5. S upon 2s is equal to 4. So I just need to solve for s now and multiply both sides by 2 upon 5. So I'll get 8 upon 5 is equal to s. So now I have what s is. So let's call this something like 5. Now I'm going to take the fact that s is equal to 8 upon 5 and I'm going to put it back inside my equation 4. So just to recall, my equation 4 was 1 plus s upon 2 is equal to t. And I have what s is. So I'm going to say t. I'm going to put a little implication arrow here. T is equal to 1 plus 8 upon 5 all over 2. So t is equal to 1 plus 8 upon 5 multiply by 1/2. So now I have that t is equal to 9 upon 5. This is equation, let's put this as number 6. So this is what t is. So now I have t and now I have s. So what I can do is I can put this into an equation which I did not use yet, and let's see what happens to them. Are they going to be equal, or are we going to get a contradiction? So I'm going to go back all the way to equation number 3. I'm going to substitute both s and t. So I'm going to put s is equal to 8 upon 5 and t is equal to 9 upon 5 into equation number 3. So I'll get 3 minus 8 upon 5 is equal to negative 2 plus 9 upon 5. 3 minus 8 upon 5, that gives me 7 upon 5. And negative 2 plus 9 upon 5 is negative 1 upon 5. So at this point in time, I can see that I have a contradiction. Okay, I have a contradiction. 7 upon 5 is not equal to negative 1 upon 5. So hence, we get one of the line that says hence, the lines do not intersect. Therefore, L1 and L2 are skew. Okay, so our conclusion for part 1 is that the lines are in fact skew. Of course, you could have taken any two equations different from what I took and the result would be the same. Just for completion, let's actually try it to see that we have that conclusion. So I'm going to go back to the top. I'm going to take back. So I'm going to, so maybe you could put like alternatively if you want. So remember from 1 we had, so I could write from 1, we had 2 plus s was equal to 2 by t. And we had that t was equal to 1 plus s upon 2. So instead of using equation 2 like I did, maybe you wanted to use equation 3, which is fine. From equation 3, so maybe from 3, we would have gotten 3 minus s is equal to negative 2 plus t. So I'll have that 3 plus 2, that's 5, minus s is equal to t. So let's equate, so I have t here now. I also have t. So let's equate both of them. So I could have equated the t's. I would have gotten that 1 plus s all over 2 is equal to 5 minus s. So what I'm going to do now is I'm going to solve for s. So let's multiply throughout by 2. So I'll get 2 plus s is equal to 10 minus 2s. And then transpose the negative 2s. I'll get 3s is equal to 8. So now s is equal to 8 all over 3. Okay, that's different from what we got from before. We got 8 upon 5. Okay, so let's see what we will get for t now. I'm going to put s is equal to 8 upon 3 into 5 minus s is equal to t. So I'll get 5 minus 8 upon 3 is equal to t. So that means t is equal to 7 upon 3. We got 9 upon 5 for t last time. So I'm going to put s is equal to 8 upon 3 and t is equal to 7 upon 3 now into equation 2, because that is the equation I did not use. So I'll put it into negative 1 plus 2 by s, which is 8 upon 3, is equal to 4 minus t, which is 7 upon 3. Negative, so I'll have 8 by 2, that's 16 upon 3. Negative 1 plus 16 upon 3, that's 13 upon 3. And 4 minus 7 upon 3, that's 5 upon 3. So I also get a contradiction here as well. So the result is exactly the same. Okay, doesn't matter how you decide to do it, both of them lead to a contradiction. So therefore the lines are in fact skew. Okay, so that was the end of question A, subpart 1. Now we are moving on to question, we're still on question 1A, but we're on subpart 2. Okay, so let's pull up back the question. So now subpart 2 asks us to find the distance between the lines L1 and L2. Okay, so some context here matters. So in part 1, we found that the two lines were not parallel, they were not intersecting, and they were skew. So this problem translates to finding the distance between two skew lines. Okay, and the distance between two skew lines is the distance, the shortest distance between these two lines here. Okay, so in case that you may have forgotten, remember the formula is different here, right? So just to recap, let me say that we have, so this is subpart 2. So I'm just going to say, suppose that we have two skew lines, which we do have, right? L1 and L2 are skew. So L1, just to understand, L1 is of the form, so if we understand this concept, we don't need to learn any formula. Okay, so L1 is of the form sum R1, I had S, is equal to P1, some point, plus S for my first line by some direction vector. And L2 was R2 for line 2, I had T, I have P2 plus T, P2. Okay, in part 1, we found that the lines again were not parallel and they do not intersect. So we are saying that the shortest segment that connects both of them is what we want, right? This is the perpendicular. So suppose I have some line skew here, some line, I don't know, like here. Right, so I want the shortest distance. I don't want this one here, I want the shortest distance here that connects both of them. So what does the shortest distance between these two lines actually mean? The shortest distance between two skew lines, because our lines are skew, is the length of the common perpendicular segment. So any vector, okay, so let's write any vector just to remember. Any vector from a point, let's call it okay, let's use the lines on L1 to a point on L2 is of this form. It is, I'm going to get another a vector here, something I'm just going to call it W, right? S and T is what I have, and then I'm going to from L1 to L2 is the point P2 minus P1 plus T by D2 minus S by D1. So in other words, in plain language, what I want to do here is I want to take this W here, S comma T, and I want to minimize this as much as possible, because remember, I want the shortest distance. But not only that, I want to minimize it, I want to minimize it over all the values of T and over all the values here of S. This is more of a calculus type of problem, okay? But we will use geometry because I believe perhaps it is easier to understand like this. So if we said before that the segment containing L1 and L2 is perpendicular to both lines, then its direction vector is perpendicular to D1 and D2 as well. So if let's write that, if the segment connecting L1 and L2 is perpendicular to both lines, then its direction vector is perpendicular to D1, some direction vector D1 and D2. If it is perpendicular to D1 and D2, it is parallel to D1 cross D2. So I'm going to let now this D1 cross D2 here be equal to our shortest line segment. So we need a name for this. I'm just going to call it and we know a name for this. It's called the normal. So I'm going to let this be equal to N. I'm going to say this is the direction of the shortest segment. Okay. Okay, so now we have set up more or less our understanding, right? So just to recap, what we did was we considered a vector P2 and P1 on our lines from L1, some L1 point to L2's point. We take the component of P2 minus P1 along the normal, which is our length of our perpendicular segment, right? And now we're going to try to eliminate S and T, right? Because if we have two skew lines and one of them have S here and one of them have T here, what I want is the shortest segment. Now, by eliminating S and T, what I want to do is I don't want S to have a value here. and t to have another value here, and I have a segment like this. This is no longer the shortest segment. Similarly, if s is too large and t is too small, then this is no longer the shortest line segment. So I want to eliminate them so I can have this one here, which is the shortest line segment. Okay, so distance will be equal to P2 minus P1 dotted with n all over the norm of n. N is perpendicular to both lines. This P2 minus P1, this is the projection of the unit vector. And of course, it is divided by the norm as well, right? The shortest perpendicular distance. So now we have all this information from the lines. All we have to do now is take it and put it inside this equation. If you want, you could even rewrite this as P2 minus P1 dotted with D1 cross D2 all over the norm of D1 cross the norm of D2. So in our question, right, back to the question, of course, you don't have to derive all of this. This is just for the understanding. Okay, we did all of this in class already. So P1 is equal to, from the question, let me just go back up quickly. P1 is 2, negative 1, 3. P2 is equal to 0, 4, negative 2. Let's identify D1 and D2 now. D1 is equal to 1, 2, negative 1. And D2 is equal to 2, negative 1, 1. So therefore, let's find P2. So I'm going to do some side working first instead of inserting everything directly into the formula. Okay, so P2 minus P1 is equal to, so we have 2, nothing minus, so we'll have negative 2. We will have 5, and then we will have negative 5. Okay, and what about D1 cross D2? D1 cross D2 is equal to I, J, K. We have 1, 2, negative 1, 2, negative 1, 1. So our I component is equal to 2 minus 1, that's 1. Then we will have the J component, which is 1 minus negative 1 by 2, which will give me just 2. So I'll have 2 plus 1, which is 3. And of course, the J component has a negative sign in front, so it becomes negative 3. Then we have the K component. So I'll have negative 1 minus 4, which is negative 5. Okay, so D1 cross D2 in vector will be 1, negative 3, negative 5. Now, let's dot it immediately as we're already here. So the dot product with P2 minus P1 will be, so I could write here, maybe dot product. So I'll have negative 2 by 1 plus 5 by negative 3 plus negative 5 by negative 5. So this is for the numerator. So this will be negative 2 minus 15 plus 25. So this is negative 17 plus 25, which is positive 8. Of course, on the denominator, I also have D1 cross D2, right? So I have to find the norm of that. So the norm of 1, negative 3, negative 5 will be equal to the square root of 1 squared, which is 1. Negative 3 squared is 9, and negative 5 squared is 25. So 25 and 9 and 1, that gives me 35. So let's put this directly into the formula now. So I'll have D is equal to the numerator, which we worked out here to be 8, all over the denominator, which is root 35. Okay, so this is our shortest distance for our skew lines. Okay, so now we're going to move on to question 1 subpart B. So the question reads, to derive the parametric equations, so more than one, of the line in R2 passing through the point P0 is x0, y0, and it's parallel to the vector V. Okay, so suppose that we have the following, so maybe a diagram might be a bit helpful. So maybe we have something like this. So we have y, we have x, and it says that P0 is a point here on some line L. Not L1, we only have one line, so it's L. And then we have P0 is x0 comma y0. And then it's parallel to some vector V. So I'm just going to put V because this is in this direction as well. And I also have P of x comma y. So let's just recall what the definition of a line to be described parametrically means, right? So a line in R2 can be described parametrically by R of t is equal to R0. Actually, let's describe it properly. So maybe it's going to be some position vector of a point on the line plus some scalar lambda or t by some direction vector. Okay, this is what it means. So they specifically gave us P0. So that means that we have P0. So therefore, P0 to P is equal to my scalar lambda. I keep saying lambda, but it's t here used, V. But remember that when we are finding P0 to P, it's P0 to O plus O to P. So, but remember that P0 to P is equal to P0 to O plus O to P. And from our question, we have P0 is x0, y0, and P is x comma y. So P0 to O would be x minus x0 comma y minus y0 in the direction, right, of V, because it told us that in the question, right? So let's write that down as well. The direction vector, fancy V, tells us how to move along the line. Okay, so now taking all of this information and putting it directly into our formula, or our, I guess we could call it our formula, we have x minus x0 comma y minus y0 is equal to t a comma b. That means that therefore r of t, so this part here, so this part here, this is my r0, this is t, and this is v. So it means that I skipped a line, so maybe from here it means that x minus x0 is equal to t a, and y minus y0 is equal to t by b. And then we transpose, and I make x the subject of the formula. So I get x is equal to x0 plus t by a, and y is equal to y0 plus t by b. And this is what we are looking for. So this brings us to the end of question number 1, and we're moving on to question number 2, which asks us to, so they give us a system of linear equations, and they specifically told us by utilizing row/column operations only. We have 3 things here we have to determine. Okay, so the first thing that we have to do is take these linear equations, put it in matrix form, and row reduce or column reduce as the case may be. Okay, so let's do that. So I have A, I have 0, I have 1, augmented with 1. I also have 1, 1, 0. I have 0, I have A, I have 1, I have 1. Oh, and I have A as well here. So I need a 1 here in this position here. So I'm going to take row 1 and interchange it with, let me write it correctly. So row 1 and interchange it with row 2. So when I do that, I will have 1, 1, 0, A, 0, 1, 1, 0, A, 1, 1. Okay. Now in this position here, I need to get a 0. So what I'm going to do is, I'm going to say that row 2 is row 2 minus A times row 1, right? That will give me my 0, which I want right here. If I do that, I need to get some space. So row 1 remains the same. I have A minus A 0, and nothing subtracted from A is just negative A. I have 1 minus A by 0, which will just give me back 1. And I have 1 minus A by A, which is 1 minus A squared. And then row 3 remains the same, A 0, A 1, 1. Now, I can stop here. Maybe I can inspect and maybe get some results, but why not try to get a 0 right here? Okay, so maybe I could do that by taking row 3. So I see that I have a A here and I have a negative A here. So if I maybe subtract these 2 rows, I'll be able to get a 0 right here. So I'm going to say that row 3 is row 3 plus row 2. I have 1, 1, 0, A, 0, negative A, 1, 1 minus A squared, 0, 0, 1 minus 1, sorry, 1 plus 1, that will give me 2, and then 1 plus 1 minus A squared is 2 minus A squared. Okay, so this is my quote-unquote row reduced matrix here. Now, when I look at this here, I'm seeing that I have a matrix, I have a pivot here, and everything below it is 0, right? So this is good. I see I have the number 2 here. Maybe I could divide everything by 2 and get this to be 1. But this will just change by a factor of dividing by 2, which doesn't make any sense because the information would not really change that much. The only thing that seems to be a problem is this negative A here. How do I handle that negative A? So I have 2 cases here. Either negative A here, or in fact A itself, we are speaking about A, is either 0 or it is not 0. So let's go back to the question for a second. The question says, determine the condition or conditions if it exists, so it may or may not exist, on A for which the system has a unique solution. A unique solution. So before we go a little bit further, what does it mean for this thing to have here a unique solution? So if it has a unique solution, then what I want is I want this last row here I want it to look like, so this number here, this scalar 2, corresponds to the entry that has the variable z attached to it. So this is like 2z is equal to 2 minus a squared. If it has a unique solution, then that means that I want, this is what we want. This. All right, so we want this thing to look like 2z is equal to some scalar. Okay, so we want it equal to some number, right? That is what we want it to look like. So when a itself, we're not speaking so much about a squared, when a itself is not equal to 0, if a was not equal to, if a was not equal to 0 here, then what I would get something like this. 2z is equal to, let's try the number 1. 1 squared is 1. 2 minus 1 is 1. So I'll get 2z is equal to 1. So that's fine. What about a half? A half squared is 1/4. That also gives me a proper scalar here. So it seems as though that when a is not equal to 0, this gives me a unique solution. So that is one way we could look at this, right? I know that this is only 3 marks, so we don't have to do much working. But to go a little bit further, so if you want to be complete, we could say, so this is part 1. We could say that when a is not equal to 0, we have a unique solution. We could look at this a little bit further again. The system that we had here, what is the rank of this matrix here? Okay, the rank of this matrix here is 3. And a unique solution, which we wanted for this system, happens when the coefficient matrix, that is this part here, the coefficient matrix has a pivot in every variable column. That's why when I row reduce here, I was looking to see where the pivots are. All right, these are the pivots here. The rank of this matrix is 3. So we have a pivot in every variable column. And for our matrix, we could say that the rank, so we could write the rank of A is equal to 0, sorry, is equal to 3, not 0. And this happens when negative A is equal, sorry, not equal to 0. Negative A is not equal to 0 if and only if A is not equal to 0. So that is why the solution for part 1 is that A is not equal to 0. Because as well, the three columns that we have here, these are all pivot columns. Yes, I know that we have negative A here, right? But if we put a condition on A, then we could figure out what all the other pivot columns really are. So if the rank of this matrix here, A, I'm just going to call it A, right? Let's call it A. If this rank of this matrix A here is 3, then what is the rank of the augmented matrix? Now, we have to look on the right-hand side of this matrix here, the augmented part of this matrix, which is this here. There are no contradictions here, meaning that I don't have 0, 0, like 0, 0, and 0 again equal to something like 1, right? That's an impossibility. That's no solution. So because I have no contradictions right here, then that means that the rank of the augmented matrix is 3 as well. So I could write here, if I want as extra, the rank of the A is B. Okay, let's not write capital B. We'll call the augmented sign common B. is equal to 3, which means that the nullity of A will be equal to 3 minus the rank of 3, which is also 3, which is 0. What about the column space? If we wanted to talk about the column space, I know that the question didn't ask for all of this, but it's a good idea to know how this works and all the information about the matrix. What about the column space? The column space of A is the span of all the columns of A. The rank of our matrix again is 3, right? And the 3 columns that we have here are all linearly independent, right? None of the columns here depend on the other column. It is not a scalar multiple of any other column. So the 3 columns are all linearly independent, and in fact they all span R3. So we could even say, if they ask us for the column space, we could say that the column space of A is equal to R3. So what is the dimension of the column space? The dimension of the column space of A is also equal to 3. Okay, what about the row space? Let's go back to the matrix again. Right, the row space here has the same dimension as the rank. The row space here as well is also 3. Right, I'm seeing I have 1, 1, 0, A. Well, I'm already concerned about the 1, 1, 0. I have 0, negative A, but remember we are putting a condition on A. So that's fine. 1, and then we have 0, 0, 2. So the row space as well here is equal to 3. So if they ask us, we have to study row space. Let's write it properly. The dimension of the row space of A is also equal to 3. And the row space of A is all of R3. And the row space of A, which we said is R3, exists as a subspace of R3, which means that the rows are, or because rather, the rows are linearly independent. So, in fact, I know I'm going too much inside here, but just in case to be complete, if they ask a basis for the row space, can be taken from any of the non-zero rows from after we have reduced it into echelon form. So the basis for the row space would be taking all the rows. So it will be the first row, which is 1, 1, 0. We will also have 0, negative A, 1. We have 0, 0, 2. Of course, we have to put as well here when A is not equal to 0. Okay, so these are what the column space, the row space, what did I forget? But of course, the answer that you're actually looking for stops all the way here. Okay, when A is not equal to 0. We didn't even talk about the null space. I almost forgot. Remember that the null space as well is the set of all solutions of AX is equal to 0. So since the nullity of A was equal to 0, then that means the null space contains only the 0 vector. So if they had asked us for the null space, then I forgot the null space would be just 0. Right? So there are no non-trivial homogeneous solutions. Okay? So of course, I mean, what you really want from this question, this part, is that the condition on A is that A is not equal to 0. That's it. Okay, and the answer for part B, subpart 2, which asks for exactly one solution, it's asking in mathematical terms for the same thing, right? But we wanted to see if you understood exactly what it means for the system or the condition of A to have a solution. Okay, which brings us to the last part of this question, which says infinitely many solutions. Infinitely many solutions. So this is the last part. So find infinite number of solutions. Okay, so I'm going back to the matrix one more time. I want this last row here to look like something like 0, 0, 0, augmented, and 0. Infinite number of solutions. Okay, so how can I make this happen? Now I have 2 minus a squared here. So if a was equal to 0, then I'll have 2. I have the augmented sign and I'll have 2. But what will happen to row 2 as well? In fact, let's write it out. Right, so if a was equal to 0, then my augmented matrix, well, the first row remains the same. But the second row now, I have 0. I have negative a, but we are saying that a is 0. But 0. I have 1. And I also have 1 minus a squared, which is 1 minus 0, which is 1. I'll have 0, 0. This is the number 2. And I'll have 2 minus a squared, which is 2. Now, if I take the second row, sorry, the last row, and I subtract it from 2 times the second row, I'll get all zeros here, which is fine. This is exactly what I want here. So therefore, the condition on A for part 3 is that A has to be equal to 0. Sorry, not equal. A has to be equal to 0. Okay, so this is the answer for part 3. Of course, you could have written this information any way that you see fit, right? And this is the end. I mean, if they ask you as well for the rank of this matrix, the rank of this matrix will be 2, right? The rank, not 3 like before, so not 2. The rank of this matrix will be 2 because we only have 2 independent rows now. That's why the rank of the matrix A, I'm saying that this is A, is equal to 2. If the rank of the coefficient matrix is equal to 2, the augmented matrix is also consistent and it has no extra independent rows. So the rank of the augmented matrix as well would also be 2, which means unlike before, the nullity of A, which would be equal to 3 minus the rank of A, which will give us 1. Okay, and for this question, if they ask for the column space, if what happens at A equal to 0, we just saw that we got 1, 0. So I'm looking at the columns. I have 1, 0, 0. I have 1, 0, 0. I have 0, 1, and then I have 2. So if you wanted to call this something, let me just call this something. From here, I have column 1 being equal to 1, 0, 0. Column 2 is 1, 0, 0. And column 3 is 0, 1, 2. So looking at this, I see that columns 1 and column 2 are the same. So therefore, the column space of A will just be the span of 1, 0, 0 and 0, 1, 2. That means a dimension. The dimension for the column space of A would be equal to 2. And if they ask us for the row space, well, the row space here in the first row I have 1, 1, 0. Then I have 0, 0, 1. So a basis for the row space would be the span of all linearly independent rows, which would just give me row 1. Okay, let's write that out. It would just give me row 1 and row 2. So the row space of A will be the span of all 1, 0. Okay, and a dimension of the row space would be equal to 2. All right. And of course, the null space here would be, because this is would give us an infinite number of solutions, then we would have a parameter. Okay, so what we would actually have to do here, if we had to solve this, I would have to solve the ax is equal to 0. And after I reduced it in echelon form, I had 1, 1, 0. So I had x plus y is equal to 0. I had 0, 0, 1, 0. So I had z is equal to 0. And then I would let y be equal to t. If y is equal to t, that means x is equal to negative t and z is equal to 0 as usual. So my homogeneous system would look like negative t, t 0, which will give me t into negative 1, 1, 0. So the null space of A would be the span of just this. That's it. Because a dimension for the null space would be 1. Right? Because we won't, and this makes sense because we only have one free variable, right? So this is actually, well, we actually finished the question further up. So just to recap, the exactly one solution and the unique solution in this case would be the same, which would be A not equal to 0. And for the infinite number of solutions, we would have to put A equal to 0. So finally, we are at the end of the exam now. We have one more question to do. Okay, and it's this part here. It is to use Gaussian elimination to solve the following system of equations. And then they ask us for some extra stuff like state the type of solution that exists. For example, infinite number, unique solution, or no solution. If a system exists, then give our answer in parametric vector form. If no solution exists, etc., etc., etc. Right. So of course, the meat and bones of this is just to row reduce. Right. So let's do that. Everything else is just representing the solution, right? But we have to get the solution first. So I'm going to take the matrix and I'm going to, this is part B. I'm going to take the solution, the equation. I'm going to put them in 1, 1, 1 and matrix form. You have 2, negative 1, 1, 3, negative 1, 2. Almost put 1 there for a second. I would have made things very, very difficult, right? So, of course, as usual, I need to get a 0 here. I need to get a 0 here. Okay? So I'm going to take row 2 and subtract it from 2 times row 1. And I'm going to take row 3. I'm going to add it to row 1. Let's write down those row operations. Row 2 is row 2 minus 2 times row 1. And row 3 is row 3 plus row 1. Of course, if you did these separately as well, it's fine, right? I just looking to save time. It's an examination. Of course, the examination is done now. So 2 minus 2 is 0. Negative 1 minus 2, that's negative 3. We have 1 minus 2, that's negative 1. 3 minus 6, 12, that's negative 9. I have, is this correct so far? Let me check back. All right, so negative 1 plus 1, that gives me 0. 2 minus, sorry, 2 plus 1, 3. I have 1 plus 1, which is 2, and then 6 plus 6, which is 12. It's so easy to make a mistake in one of these row operations. Okay, so now I need to get a 0 here. Okay, so I'm going to take row 3 and add it to row 2. Row 3 is row 3 plus row 2. So 1, 1, 1, 6. I have 0, negative 3, negative 1, negative 9, 0, 3 minus, sorry, 3 Yes, 3 minus 3, that's 0. I have 2 minus 1, that's 1. And I have 12 minus 9, that's 3. Okay, I do not need to reduce anymore because I'm seeing that I have z is equal to 3 here, or z, as the case may be. Right, so maybe I can back substitute and get some solution. So it looks as though I'm already getting a unique solution. So I could say from row 3, I have z or z is equal to 3. So I already have what this variable is. I'm going to put z is equal to 3 into row 2. So I could say from row 2, I have negative 3y minus z is equal to negative 9. Negative 3y minus 3 is equal to negative 9. Did I do this correct? So I have negative 3y is equal to, carry this on the other side, I get negative 6. So that means y is equal to positive 2. So now take z is equal to 3 and y is equal to 2. And we're going to put this inside row 1, which reads x plus y plus z is equal to 6. So I have x plus 2 plus, what was that again? 3 is equal to 6. So I'll get 5 plus x is equal to 6. That means x is equal to 1. So we have a unique solution. Okay, and this brings us to the end of coursework number 1.